So let's talk about how the gases are actually transported in the blood. So how does the blood carry the oxygen and the carbon dioxide? So it's, of course, it's not as easy as we think. Okay, so the first thing is oxygen. So let's do oxygen. So the blood's ability to transport oxygen depends on the solubility coefficient of oxygen. So oxygen does not dissolve well in water. Okay, it just doesn't. Okay, so it's very low. So very little oxygen is going to be dissolved in the plasma. Okay, so what we have to think about is how else can it be carried? And I think you guys know this. It's going to be carried in hemoglobin. Okay, so oxygen's going to attach to the iron of the hemoglobin. So 98% of the oxygen in the blood is bound to hemoglobin. The other 2% is going to be dissolved in the plasma. So we abbreviate hemoglobin HB. Okay, so it's easier than writing out hemoglobin. So HbO2. So HbO2 is oxyhemoglobin. So that's hemoglobin that's carrying oxygen. Okay, after hemoglobin stops carrying oxygen, if it carried it before and it doesn't carry it, it's called HHB. So HHB is deoxyhemoglobin. So it's hemoglobin that's given up its oxygen. So once hemoglobin binds the first oxygen molecule, it modifies its shape so that it can pick up the other three more easily. Okay, so I just told you, so hemoglobin can bind 4 oxygen molecules. Okay. Now, the oxyhemoglobin dissociation curve. Okay, so that's a mouthful, isn't it? Okay, so basically what it's saying is the percent saturation of hemoglobin increases as the partial pressure of oxygen increases, which that makes sense, right? So if you increase oxygen, you increase the amount of oxyhemoglobin. Okay, now, if you look at this graph, it's kind of interesting to see. Okay, so here's at 60 millimeters of mercury as the partial pressure. So if you look here, after 60, okay, after the partial pressure of 60, okay, the hemoglobin can't really carry that much more oxygen. Okay, so if the partial pressure of the air is 60, we're probably carrying about as much hemoglobin as we could possibly carry. Okay, so like when you get up to 100%, it's like 98. Okay, so you can only carry so much hemoglobin or oxygen on your hemoglobin. So you can't, it doesn't matter if you're inhaling pure oxygen, you can only saturate it so much. So think about the athlete inhaling pure oxygen on the sidelines. Okay, so it would be close to, the pressure would be like 100. Okay, if they are at regular sea level, okay, they're already going to be super saturated. Okay, so this 100% oxygen isn't really making that big of a difference. At the lower levels, okay, it's going to affect it. Okay, now how's carbon dioxide transported? So it's transported dissolved in plasma. Okay, so CO2 dissolves in water. So think about soda. Okay, so think about soda. It's carbon dioxide that makes the bubbles. Okay, it dissolves well in water. Okay, so 7% that. Some of it is attached to the amine group in the protein in the hemoglobin. Okay, so it's not competing. It's not competing with oxygen for the iron. Okay, it's binding to a totally different place. It's binding to the protein, okay, which is the amine group of the globin part. Okay, so they call that, this is like one of my favorite words, carbamina hemoglobin. Okay, so HbCO2. Okay, now The last part, okay, is it's carried as carbonic acid. So as bicarbonate dissolved in water or in plasma. Okay, so it's going to look like HCO3 negative. Okay, and we're gonna go over that equation again that we've talked about before. Okay, so it can be carried like that. That's like 70%. What's the other 70%? All right, now this this picture has, it looks kind of complex, but it's actually not that bad. But what we want you to get you to see, okay, is how carbon dioxide binds with water. Okay, and that's going to give us H2CO3, which is carbonic acid. Okay, now there is an enzyme found in your red blood cells that takes care of that. Okay, so the enzyme is called carbonic anhydrase. Okay, so it's found in our red blood cells. Okay, now this molecule is not very stable. Okay, so it splits, and I didn't give myself enough room. It splits, I'm going to go down here, to HCO3 negative plus a hydrogen ion. Okay, now if you remember from before, we've said that this this equation can go, it's reversible, it can go either way. Okay, so here's what happens. Okay, so carbon dioxide comes from the tissue. Okay, it's going to come into the blood. It binds with water. Carbonic anhydrase converts it to carbonic acid, and that splits. This hydrogen ion, okay, is actually going to bind to hemoglobin. Okay, the bicarbonate, okay, can come out and be carried in the blood. Okay, now we have to account for this bicarbonate because it's charged. So what happens is a chloride ion that's outside of it actually is swapped, and that's called a chloride shift. Okay, so that's what happens to the carbon dioxide and how it gets converted and carried. Okay, now when we go to, if we're at the lungs, okay, and we're going to drop off CO2. Okay, we need to get it out of the blood. So what will happen, okay, is the bicarbonate enters the cell, okay, and it combines with the hydrogen ions. Okay, we're going to do another chloride shift. We'll get rid of the chloride to neutralize the charge difference. Okay, so hydrogen ion and HCO3 come together. They make carbonic acid. Carbonic anhydrase breaks this down into carbon dioxide and water, and then carbon dioxide can cross the respiratory membrane, and then it gets exhaled. Okay, so I think it could be this kind of image simplifies it. So just remember, this is what's happening at the tissue, okay, and the systemic capillaries, how we pick up CO2. And this is what's happening at the lungs and how we get rid of CO2. Okay, so here's it written out. Okay, so carbon dioxide loading, carbonic anhydrase is the enzyme that's found in the red blood cells that catalyzes the reaction of CO2 plus water. Okay, so that's carbonic anhydrase. The chloride ion shifts to kind of like neutralize the charge of losing this HCO3 negative. Okay, now oxygen unloading. Okay, when the hydrogen from here binds to the hemoglobin, okay, it kind of kicks off this oxygen. Okay, and then the oxygen can be unloaded to the tissue. Okay, now what is really interesting, okay, so unloading means we're going to the tissue. Okay, so we're dropping it off at the cells that need it to do cellular respiration. Okay, hemoglobin in the blood, it arrives saturated at 97%. When it leaves and the blood is blue, it's still 75% saturated. Okay, so we still have a lot of oxygen in our blood. Okay, so we call that venous reserve. Okay, so there's still some in there. It buys you a little bit of time if you're not breathing. Okay, so we've released about 22% of the oxygen when we drop it off. Okay, now what affects how the oxygen is dropped off? So the first thing is how much oxygen is actually in the tissue. Okay, so if the tissue is active, it's using the oxygen. Okay, so you need to drop off more oxygen. Okay, so if tissue is active, the temperature is increased, so more oxygen gets dropped off. If the tissue is active, it has a higher carbon dioxide level, which means it has a higher hydrogen ion level, and that lowers the pH. Okay, when the pH drops, you unload more oxygen. Okay, another molecule is called bisphosphoglycerate, or BPG. Okay, if cells are using lots of oxygen and they go into anaerobic respiration, this molecule triggers the release of oxygen. So it's just 4 different ways that we can regulate how much oxygen is dropped off to tissues.